Hello, very good morning. Hope you are all safe and taking care of yourself and the other members of your family also. So, keeping the odd semester examination pending in compliance of university calendar of events, we are commencing the even semester classes, of course, virtually through online. I don't know to what extent the online classes are beneficial for students because of some technical issues. In some remote rural areas, the access of internet is a problem. Anyhow, for that sake, usually I am not giving live streaming. I will put in Google Drive and I will send the link. You can access whenever, wherever you feel free and network is available. Okay, for this semester, for both the divisions, I am common. That's why in regular online timetable, I have not put my slot. You are having weekly 5 periods, but I have given only 4 periods, taking other subjects into consideration. Weekly one time, combinedly, I will post the link of my class for both the divisions. And for this semester, I am entitled to take the first unit of fourth semester. The first unit is interference, interference of light. In the previous semester, you have studied geometrical optics, which deals with image formation and which uses rectilinear propagation of light. That's light travels along straight path. Whereas for fourth semester, you have wave optics, that is physical optics. Light travels in the form of waves. Of course, the elementary idea about light you are having. What is light? Light is a form of energy which help us to visualize the objects surrounding us. In fact, light is invisible, including light, because light is electromagnetic energy, electromagnetic wave, and you have a huge family called electromagnetic spectrum, right from radio waves, infrared, visible, ultraviolet, X-rays, gamma rays, cosmic radiations. All these, they are invisible. Now you are receiving a signal through this mobile. So mobile is receiving electromagnetic signal which is invisible. In the same sense, light is also invisible. It makes us to see the objects surrounding us. What is actually happening? Light coming from a source, for example, the sunlight or a light from an electric bulb, it fall on object. The reflected light enter our eyes. Eye is acting as a lens. It is a lens system only, and through optic nerve it goes to the master control brain, and brain recognizes, it reckons this is this object, this is book, this is pen, this is pencil, like that. Suppose if you close your eye, you do not see anything. So our eye is the entry point. The reflected light it receives and brain recognizes what type of object it is, right? So that is about a light. So coming to the portion, I will put the entire syllabus later, and my portion 15 hours theory and 3 hours meant for problems. So 15 plus 3, 18 hours, weekly one period, but your semester system itself is a 16-week program, including conducting 2 internal examinations, and in between some days on which my period is allotted, maybe a government holiday or any disturbance we may have. So 18 hours that is prescribed, but hardly we may get 10 to 12 classes. Anyhow, in this online, I don't know, because for teaching physics, chalk and talk is always a best method. So I will just I may take 2 to 3 periods through online, and it will be more convenient when offline classes starts. Of course, interference applied to have studied at PU level also. Here straight away our syllabus begins with Fresnel's biprism. There are 2 types of interference due to division of wavefront, in which Fresnel biprism and determination of wavelength of monochromatic light, as well as the thickness of a thin film using biprism. That is the first part of this unit 1. In the later part, interference due to division of amplitude. The entire remaining portion is of second category, division of amplitude. The basic Stokes theorem, Stokes treatment of reflection and transmission at an interface. Then study of thin films, thin film interference, conditions for maxima and minima. In case of reflected light, a huge derivation is there. Multiple reflections, mention of conditions for maxima, minima. In the case of transmitted light, there also you have a derivation. Exhibition of colors by thin films, qualitative discussion of wedge shaped film with mention of expression for path difference. That's a qualitative treatment, not quantitative. And very important, theory of Newton's rings and determination of wavelength of monochromatic light using Newton's rings. Michelson's interferometer, formation of circular and straight fringes, qualitative, and determination of wavelength of monochromatic light using Michelson's interferometer, and standardization of meter. These are theoretical part, and problems, as I mentioned, 3 hours. So since it's a huge portion, last I have put in a blue color from Michelson interferometer. So that portion has to be taken by faculty who is dealing electromagnetic radiation, because the duration for electromagnetic radiation is around 8 to 9 hours, whereas here it is almost double. Okay, so some arrangement we will make, because as far as the reference books are concerned, of course you are all familiar since from previous semesters. I am not going to recommend the books which are written in accordance with the syllabus of university, but the standard books are Principles of Optics, B.K. Mathur, a good old book; Fundamentals of Optics by Khanna and Bedi, a textbook of optics, Brijlal Subramaniam, this is the best book; Optics by Ajay Ghatak. If you switch over to master's degree, you have to refer this Ajay Ghatak book only. Fundamentals of Optics, Jenkins and White. It's of course foreign authors. And recently, Modern Optics by A.B. Gupta. This is also a good book. So I prefer Brijlal and Subramaniam and A.B. Gupta, and here and there I also use Mathur, Jenkins and White also. Of course, Khanna and Bedi you have referred for sound portion, simple harmonic motion and sound in first semester and second semester. Okay. Today just I will refresh what you have studied at PU level, the basic information, and after the class maybe within half an hour after posting this PowerPoint presentation, I'll give one or two videos, just small videos about 9 to 10 minute duration, which give you visualization of the phenomena of interference, as well as how wavefront, primary, secondary wavelets. So that idea you will get through those visuals. Okay, let's start the basic idea. You know, for interference to take place, two or more light waves superimpose. The resultant amplitude or intensity in the region of superposition is different than that of individual waves. So the phenomena in which the modification in the redistribution of intensity of light in the region of superposition is called interference of light. But first you should understand what is principle of superposition, because principle of superposition is common. You have studied in sound also, superposition of waves. Okay, that is principle of superposition. I'll come back to that, and this is a table which is showing the weightages. So for which chapter what is the weightage? So the first unit is interference, 15 hours, problems 3 hours. You see, in all categories of your question paper, in a 2 mark you have 3 category MCQ, multiple choice questions. So totally 4 questions will be there. Out of 4, 1 question belong to this interference, and theoretically 4 questions will be there. So 1 from interference, and 2 mark numerical problems will be there, totally 4, out of which 1 coming from interference. And as far as 5 marks, 1 theory and 1 problem from interference, and you have 4 questions each in the theory and problem section. And as far as a 10 mark question, you have a bumper here, 2 questions coming from interference. So totally your question paper will be designed for 124 marks, including all choices, and 36 marks out of 124 coming from interference. Of course, you are answering for 80 marks. So in 80 marks, if you are perfect with interference, you will get 36 marks. Okay. So I have put in different colors the other topics. The second faculty has to take diffraction, in which 2 classes are there, Fresnel class and Fraunhofer class. Together it is 13 hours duration, and this is the distribution. And here for first category 9 marks and 22 marks for second class. So both together 31 marks. That's the second largest portion, diffraction. And as far as polarization, it is just 8 hours, and you will get 19 mark questions. And thermoelectricity, it is dealt by the 4th person, 19 marks out of 9 hours. And electromagnetic theory, which is 8 hours duration, again 19 marks out of 124. So you can observe the duration allotted as well as the marks distribution for these units. So you can observe only interference and diffraction more than 10 hours. So it is 15 plus 3, whereas here it is 13 plus 3, almost 16 hours, and this is 18 hours. So remaining very less. Thermoelectricity 9 plus 2, 11 hours, no problems from polarization and electromagnetic theory, so 8 hours. So because of this heavy load, so the teacher who is taking electromagnetic theory has to take Michelson interferometer. Okay. So coming back to superposition, principles of superposition. In principle of superposition, if two or more light waves, in case of sound waves, two or more light waves of same frequency overlap, superimpose at a point, the resultant effect depends on the phases of the waves as well as their amplitudes. The resultant wave at any point, at any instant of time is governed by the principle of superposition. The combined effect at each of the region of superposition is obtained by adding algebraically the amplitudes of individual. Let us assume here in this diagram the component waves are of same amplitude. That is, this is the first wave, and you know one complete wave means, suppose the wave starts from here, it reaches maximum and then returns to mean position, goes to other side, reaches maximum and it returns. So this is complete one wave, right? So in longitudinal, one compression and one rarefaction forms one complete wave. A sound wave is longitudinal wave, whereas transverse wave, one crest and one trough, that is a elevated portion and a depressed portion. This is one complete transverse wave. Light waves are electromagnetic and they are transverse in nature. So we will talk in terms of crest and trough. This is one complete wave. Now in this diagram, this is one wave train, this is a second wave train. So when these two superimpose at a point at the same instant of time, the resultant is the algebraic sum. Suppose the first wave is having amplitude. Amplitude, you know, the maximum displacement away from mean position of rest. So this we call it as a peak. So the peak is situated at what distance from mean position? That is called amplitude. So amplitude of first wave is A. The amplitude of second wave is also A, because we are considering two component waves which are having the same amplitude. So the resultant wave is different from individual wave. Here, if the waves are arriving in phase, so in phase means attaining maxima and minima at the same instant of time. You can observe these two are identical in all respect. You see how many complete waves are here. This is 1, 2, 3, 4, 5 and 6. 6 and a small portion is there. This is also same, 6 complete waves and a small portion. They are identical, and where the first wave is attaining its maxima and minima, at the same instant the second wave is also attaining its maxima and minima. So when these two identical in all respect waves superimpose, overlapping one over the other, the resultant wave will have an amplitude which is algebraic sum, A plus A, it will be 2A. So amplitude of this wave is 2A on positive side, 2A on negative side. So this is redistribution in the intensity of two interfering waves. This is called interference. Whereas in the second diagram, that is B, waves are identical, amplitude also the same, frequency is also same. Frequency is what? Number of this type of waves in 1 second, how many are there? So the same, but as far as phase is concerned, the second wave is out of phase when compared to first wave, because at what instant the first wave is attaining its maxima, at the same instant the second wave is attaining its minima. So they are totally out of phase. Okay, And as far as phase is concerned, you can express in terms of time interval or in terms of phase angle. Okay, suppose here this is 0 instant, the phase angle is also 0. So when it is attaining maxima on positive side, now it is taking quarter the time period, that is t by 4, or in terms of phase angle it is 90 degree, that is pi by 2. And when it returns to mean position, here it takes what? It takes half the time period, that is t by 2, and phase angle is pi radian or 180 degree. And when it goes to other side maxima, the time taken is 3 times quarter the time period, that is 3 t by 4, or the phase angle in this case is 270 degree or 3 pi by 2. And when wave is completely covered returning to mean position of rest, it is taking complete time period, that is time taken for one complete oscillation, it is capital T. And the phase angle in this case is 2 pi radian, that is 360 degree. So for one complete wave, 360 degree or 2 pi radian is what? It is the phase difference. So difference between the 2 points which are in the same state of vibration, the phase is 2 pi radian, or the phase difference between two consecutive points which are in same state of vibration, that is the crust. This is 2 pi radian. Trough is also 2 pi radian. And this is one complete wave. So length of one wave is called wave length. Okay, it is nothing but distance between two successive points which are in same state of vibration, same phase. So distance between consecutive crusts or consecutive troughs is nothing but wavelength, which is denoted by lambda. That is called path difference. Okay, so distance between crust to crust, trough to trough, which is path difference lambda, is equal to phase difference 2 pi radian. So lambda is equal to 2 pi. Understand? Path difference and phase difference. Okay, and in this case, since they are out of phase, so where crust is there, at the same instant you have a trough. So when they superimpose, the resultant will become what? Algebraic sum you are taking. This is plus a and this is minus a. So they vanish as 0 amplitude. It is happening at every instant. So nothing will be seen here, no wave. So in the interference of light, wherever you have enhancement in the amplitude after superposition of wave, you will have bright region, bright fringe. Wherever you have the superposition of waves which are out of phase, you will have a dark band, a dark fringe, because a minus a, it is 0. So nothing will be seen, nothing will be formed. So in interference, when waves arrive at a region in phase with each other, there you will have a bright band, and wherever you have the waves which are superposing out of phase, you have dark band. So in the region of superposition, you will find alternate bright dark bands, that is fringes. That is the interference which you have studied at PU level, the principle of superposition. Okay, so as I mentioned, I just recall, when two light waves superpose, the resultant amplitude or intensity in the region of superposition is different than that at that of individual waves. So the modification in the redistribution of intensity of light in the region of superposition is called interference of light. When the resultant amplitude is sum of amplitude of two individual waves, the interference is known as constructive interference. that is A plus A. When individual amplitudes are added up, it happens only the super or interfering individual waves as they arrive in phase. So such an interference is called constructive interference. So constructive interference is a bright band of light which is observed at points of constructive interference. And when the resultant amplitude is the difference of two amplitudes, that is A minus A, in that example, the interference is known to be destructive interference. You have appearance of a stationary dark band of light at points of destructive interference. So two types of interference, constructive interference and destructive interference. When waves superposed, if they are in phase with each other, the algebraic sum of amplitudes of interfering waves, so added up, the resultant is a bright band. So wherever you have a bright band, constructive interference. Wherever you have a dark band, that is called destructive interference. That is because of interfering waves with opposite phase. They are out of phase, they are interfering. So two or more coherent waves. You should recall the meaning of coherent. So two or more coherent waves of light, when they are superposed, the resultant effect is brightness in certain regions and darkness at other regions. That brightness constructive, darkness destructive. The regions of brightness and darkness may take in the form of either straight bands, that is fringes are straight, or they may be of circular rings. You have Newton's rings and you are going to perform the experiment also in the laboratory. You are practically you are going to experience circular rings or other complex shape. So other complex shape means either elliptical, parabolic, hyperbolic fringes depending upon the situation. The alternate bright and dark bands are called interference fringes. The phenomena of redistribution of light energy due to superposition of light waves from two or more coherent sources is known as interference. So you should understand the meaning of coherent sources, and that is a very primary and fundamental condition. The sources must be coherent. What is the meaning of coherent sources? I have given the definition here. So coherent sources of light are those sources of light which emit light waves of same wavelength, frequency, and in the same phase, are having constant phase difference. That is, the two sources must emit radiations of same color or wavelength. So since you did the experiment with the spectrometer, you are familiar. So wavelength is characterized by color. So color is nothing but wavelength, wavelength is nothing but color. So the two sources are said to be coherent if they are emitting light waves of same frequency, same intensity, same wavelength and same phase. Understood? So such sources are called coherent sources. In fact, the individual lamps, they are not coherent sources even if specifications are same. For example, if I have a 40-watt bulb of a Philips company and another 40-watt bulbs of the same Philips company, when I switch on both, they may not give light radiations of same wavelength, same frequency and same phase. It is very difficult to have exact coherent sources. Individual sources cannot be treated as a coherent. So we used to derive coherent sources from the single source only. Okay, so I will explain in the next slide. So two independent sources of light cannot be coherent. The reason for this is the light emitted from individual atoms when they return to ground state after being excited either by heat or electric discharge. Even a smallest source of light contains billions of such atoms, which obviously cannot emit light waves in the same phase. So you have seen in the laboratory while performing experiment with the spectrometer. So there in a calibration of spectrometer or in dispersive power and dispersion curve you have plotted. There you have used mercury source, right? So you have taken so many colors, wavelengths are different, right? For example, if you take yellow lines, you have 2D lines, yellow 1 and yellow 2. For mercury, it is 5770 angstrom and 5790 angstrom. So difference in these two wavelengths is 20 angstrom. Whereas if I take sodium vapor lamp, which is monochromatic, though it is a monochromatic, it gives 2D lines. Means when sodium vapor lamp light is allowed to pass through prism, again you will get yellow doublet, yellow 1, yellow 2. But what about the wavelength? Is it same 5770 and 5790 angstrom? No. In fact, it is 5890 angstrom and 5896 angstrom. The difference between those two wavelengths is just 6 angstrom. What's the reason? Because in any system, when that element is get excited, means inside the atom, the electron get excited. It goes to different higher energy levels and it cannot stay for a longer period. Within nanosecond, it has to return. So when it returns, so from which higher energy level to which lower energy level the transition of electron is taking place, that emit an electromagnetic radiation of a particular characteristic color. Characteristic color means characteristic wavelength. Understand? So mercury atoms which are producing yellow lines, their wavelength is entirely different because characteristic. ಅದೇ ಆಟಮ್ ಇಂದೆ ಲೈನ್ ಬಂದಿರ್ತದೆ, right? Whereas sodium atoms which are transiting from higher to lower giving those wavelengths 5890 angstrom and 5896 angstrom, they are different. So in the same bulb, the atoms which are get excited to different extent, when they return, they may not radiate the same color. Understand? Because transition between which higher energy level to which lower energy level, all atoms may not return to same ground state, right? So that's the reason. So two independent sources of light cannot be coherent. So two coherent sources, if I call A and B, can be obtained from a single source of light either by using property called reflection, refraction, etc. This is because all random phase changes occurring in parent source are repeated in the two sources A and B. So if A and B are the two sources derived from the same single light source, whatever the changes are taking place in the primary source, the same changes will be obtained in the secondary sources A and B. So that there exists a constant phase difference between light emitted from A and B. That is the idea about the coherent sources. Let us understand what is meant by wavefront and what is the ray. Of course, in geometrical optics, you have used direct linear propagation of light. Light travels along straight path. So that path is indicated by a straight line. The direction in which light is propagating is indicated by an arrow. That is geometrical optics. Okay, but here you are using wave concept. Light travels in the form of wave. So waves start from the source and spread out into new and new regions of space. Suppose if you imagine there is a still pond, the surface of water is quite calm. Suppose if you drop a pebble or any object, a stone, what happens? as soon as it touches the surface of water, that is point of disturbance. Of course, the stone or pebble is moving in the downward direction, but from that point outward, you are having concentric circles spreading towards the shore of the pond, right? The same circles from the light source, the similar sense, they are also originating, just like the ripples on a water surface start from point of disturbance and expand in the form of circles. The circles are in fact the crest of the waves, the elevations. The circle what you are observing, it is a elevated portion of a water surface, that is crust, and again depression, that is trough, again a circle, that is crust. So alternate crust what you are observing and spreading out from the point of disturbance. So all the particles which are located under the crust will be in the same state of vibration, the same state of oscillation. Therefore, on points on such circles, they are in same phase, the same state of vibration. Okay, so what is wavefront? The continuous locus of all particles which are in the same phase is called a wavefront. So in the ripples of water, the particles on the circular ring which is formed, originated from point of disturbance, they are all in phase. I'll show one diagram. A surface which passes through these points and completely surrounds the source is called the wave surface. So around the point of disturbance, you are concentric circles. So on each circle, the particles are in same phase, and the surface which passes through these points and completely surrounding the source known as wave surface, wave front and a wave surface. So in case of water ripples, the wave fronts are the circles, whereas in the case of a point light source, they are all spheres. So in the diagram, the wave fronts I have shown. I will come back. So in the diagrams, the wave fronts are often shown connecting crests or troughs. But in fact, any surface connecting points of equal phase in a wave front, the propagation of the wave front is visualized by advancing the wave front, and a stationary wave surface is followed behind it. The wave surface are separated by one wavelength. So you are finding a circle around a point source. On the circle, the particles are in the same state of vibration. So a surface which passes through all these points is considered as wave surface. So wave front, wave surface. Okay. So propagation of wave front is visualized by advancement of a wave front, and the stationary wave, it is behind the wave front only. So the wave surface are separated by one wavelength, that is separation between one wave surface and another wave surface, that is one wave front and a next wave front, is nothing but one wavelength. That is nothing but what? Separation between consecutive crust only or trough only, that is elevation, depression you are finding. That is what it is shown here. You can observe these are the circles. Okay, so surface is the points which are in the same state of vibration, they passes through this particular region. Okay, and here, so here crust, here also crust, and here in the gap troughs will be there, right? So they are separated by one wavelength denoted by lambda. So you are observing these are the wavefronts surface containing same points of which are having same state of vibration. So this is wavefront, this is wavefront. So behind the wavefront the wave surface is following, and you are observing the advancement of the wavefront. So in which direction it is propagating, so that is indicated as the ray. So at considerable distances from the source, a spherical wavefront becomes very large. So as it advances and when it moves certain considerable distance from the origin, almost it looks like a plane wavefront. Now in the beginning you are observing circles, but as it proceeds you are getting at a larger distance, almost it is plane for a certain region. Of course the circle will be there, right? At one particular position you are observing it looks like a plane wavefront. So a small portion of it may be considered to be nearly planar. So this is what in figure B it is indicated. In that case it is called a plane wavefront. It is sometimes more convenient to describe the wave propagation in terms of rays instead of a wavefront. A line drawn perpendicular to the wavefront is called a ray. It shows the direction of propagation of the light. So a line drawn perpendicular to wavefront is called a ray. It shows the direction along which the wavefront moves. So that is from here afterwards we speak light travels, though it is indicated by a ray of light. So that a ray of light is an indication of propagation of wavefront. In fact, perpendicular to wavefront a line is drawn just to indicate in that direction propagation of wavefront is advancing, moving in a forward direction. And this is about wavefront. These are all elementary and that you have studied at PU level. And what is the condition for sustained interference? And just now you understood interference, you need coherent sources, and you know the meaning of coherent sources. So simple conditions are there. The two sources of light must be coherent for interference to take place, and it should be of a sustained interference. So sustained interference means clear, bright, dark, sharp fringes you should notice. Okay, so you have seen the spectra in spectrometer. If all arrangements are proper, adjustments are proper, then the spectrum pattern will be sharp lines, bright colors, very straight, very fine, sharp behind a dark background, right? So for interference fringes to appear in that sense, your sources must be coherent. As I mentioned, you cannot have two individual coherent sources. You should get two coherent sources derived from the same single source only. The light emitted by two sources must be monochromatic. So chrome means color, mono means single. So light source must be monochromatic. The white light is not monochromatic, it is polychromatic. It contains so many colors. Mono, single color. So for example, sodium vapor lamp, it gives single color yellow. It is a monochromatic. And laser light, it is also highly monochromatic, right? The amplitudes of two interfering beams should be equal. So this condition, it is because at where the waves are interfering in phase, the amplitude will be added up. Okay, when compared to individual, it will be doubled as far as amplitude, whereas intensity is always proportional to square of the amplitude. So A plus A, the resultant amplitude is 2A, square of that, it is 4A square. If I take A square as intensity I naught, I is equal to 4a square, that is equal to 4I naught, right. So, and if amplitudes are equal, wherever the destructive interference, the dark band you are observing, it will become a perfect dark band, because A minus A, it is 0, nothing will be there. If they are unequal, you will have a blurred and a faint brightness also you can see. So, to avoid that, the amplitudes of two interfering beams should be equal, and those two coherent sources must be narrow. So, you have seen, if in the spectrometer, if a slit is not narrow, what happens? You will have blurred spectrum, right. So, it should be as narrow as possible, so that you will get sharper lines. And here also, for sharper interference, for a sustained interference, the sources must be narrow, and these sources must be close to each other, just within 1 mm, within 1 millimeter, within 1 millimeter, or the separation between two coherent sources must be of the same order as that of the wavelength of light. You know, wavelength of light is in the order of angstrom. Okay, so 1 angstrom is 10 to the power minus 8 centimeter, or 10 to the power minus 10 meter, in that order. So, the separation between two slits must be in microns, so in the millimeters, right. The screen should be at a larger distance from coherent sources. So, where you are observing the interference pattern, that itself is taken as a screen. You can take a white wall at a distance more than 1 meter, or if you are observing through eyepiece, that eyepiece should be kept around 70-80 centimeters, or even 1.5 meter. Okay, and these are basic conditions for constructive and destructive interference, that also you have studied at PU level. Conditions for constructive interference in terms of phase difference, and condition for destructive interference. Okay, here it is shuffled. So, condition for constructive interference is, if I take phase difference denoted by pi, and pi should be equal to 2 pi n, and you know 2 pi is equal to lambda, that is the path difference and a phase difference. So, for a path difference of lambda, phase difference of 2 pi will be there. So, if it is where n is integer, takes the values 0, 1, 2, 3, this is for constructive. For constructive interference, it should be integral multiple of full wavelength, integral multiple of lambda, whereas for destructive interference, now this equation, it should be here, okay, the phase difference, okay, and now for this equation is for destructive interference, it is 2n plus 1 times pi, where n is again 0, 1, 2, 3, when n is 0, pi, when n is 1, it is 2 pi, 3 pi, like that. Or in terms of path difference, it is odd multiple of half the wavelength, right, odd multiple of lambda by 2. So, when n is equal to 0, it is 1 into lambda by 2, lambda by 2. When n is equal to 1, 2 plus 1, it is 3, 3 times lambda by 2. So, lambda by 2, 3 lambda by 2, 5 lambda by 2. So, odd multiple of lambda by 2 for destructive interference. For constructive interference, it is integral multiple of the wavelength. Okay. So, you should remember these two conditions. Constructive means bright. Condition for bright band, integral multiple of wavelength, and for destructive, that is dark bands, it is odd multiple of half the wavelength. So, your syllabus starts from here afterwards. In fact, your syllabus begins from Fresnel's biprism. Still, we are discussing how to obtain coherent sources, methods of producing coherent sources. The phase relation between the waves emitted by two independent light sources rapidly changes with time, and therefore they can never be coherent. I mentioned the reason for that. Though the sources are identical in all respect, because the light what we are getting, it is because of an atom excited, and when it returns, it radiates an electromagnetic radiation depending upon the source. Mercury atoms, sodium atoms, hydrogen atoms, and in case of a tungsten filament lamp, the tungsten filament is get heated. So because of this heat, the atoms of are get excited, and when they return, they radiate radiations of their own wavelength. Understand? So we should derive a single source to obtain two coherent sources. So in practice, two sources are derived from a single source by some device. Of course, we are using either the property of reflection or refraction. Then any phase change occurring in one source is simultaneously accompanied by the same phase change in the other source, because both sources are derived from a single source only. Therefore, the phase difference between the waves emerging from these two sources remain constant, and sources are coherent. The techniques used for creating coherent sources of light can be divided into following two broad classes. So there are two classes of interference. Interference produced by division of wavefront. That is, the main idea is to obtain coherent sources, and interference by division of amplitude. So two broad classes are there. Let us study what is interference by division of wavefront. And you know the meaning of wavefront already now. The incident wavefront is divided into two parts, either by utilizing phenomena of reflection, refraction, or diffraction. And these divided two parts of the same wavefront travel unequal distances, and they are made to reunite at some angle to produce interference bands, and this is known as interference by division of wavefront. So the wavefront coming from the primary source is divided into two parts or any number of parts, either by phenomena of refraction, reflection, or diffraction. And these divided parts, they are traveling unequal distances, and they reunite at some angle, or they are made to superpose at certain point to obtain interference bands. So such a interference is known as interference by division of a wavefront. And the Fresnel biprism, that is a very first topic from where your syllabus begins, and Lloyd's mirror, these two, they use the principle called interference by division of a wavefront. They are the examples of this class. Whereas division of amplitude, the amplitude of incoming beam from the primary source is divided into two parts, either by parallel reflection or refraction. And these derived or divided parts, they reunite after traversing different paths, and they are made to superpose to produce interference. So such an interference is known as interference by division of amplitude. In this case, a point or a narrow line source is not required, not essential, but a broad light source is employed to produce brighter bands. So broad light source in the laboratory, we will achieve what you are observing, a rectangular box, hollow box. Rectangular slits are made, and the interior you have a bulb. You have seen a mercury bulb is covered with a rectangular wooden box, and a narrow rectangular slit we used to have, that is called a broader light source. And at home you are using tube light and all these lights, we call them as a extended sources. Extended sources are nothing but broad light sources. So such type of sources we require to obtain interference by division of amplitude. And Newton's rings and Michelson interferometer are the examples of this class, and both you are learning in the theory as well as in the laboratory. You are going to perform Newton's rings. Of course, Fresnel biprism is also there, but our Fresnel biprism, I'll tell you what's the problem to set up. Okay, so up to here I have given the introduction which you have learnt at lower classes. From Fresnel prism biprism onwards, you have commencement of your syllabus for the 4th sem. Just I will tell you what is Fresnel biprism and I will wind up. So Augustin Jean Fresnel, a French physicist, he constructed this biprism. The name itself is saying it consists of two acute angled small prisms which are joined base to base. Okay, so Fresnel biprism is essentially a combination of two acute angled prisms placed base to base. In practice, this combination is obtained from an optically plane glass plate by proper grinding and polishing. Of course, according to definition, two acute angled prisms are to be joined base to base. You know prism, you have seen the prism, equilateral prism you have seen in the laboratory. Each edge is having a 60 degree, right? You know base and polished surfaces also. But in this case, we have to take two acute angled prisms. They are to be joined base to base to obtain a biprism. But in practice, we never do like that. In practice, we will take a single transparent glass plate with the proper grinding. With the proper grinding and polishing, we used to get a biprism. Okay, the obtuse angle of the prism is about 179 degree. You know, angle of a plane is 180 degree. Now here, the obtuse angle of this biprism, that is refracting edge, in this case is 179 degree. You did experiment in the laboratory where equilateral prisms you have used and refracting angle is 60 degree. Where polished faces are joined, the angle subtends 60 degree. But here the angle subtended where the polished surfaces are joined, it is 179 degree. That's why it is more convenient, rather than taking two separate acute angle prisms joining base to base, instead a single plate whose angle is 180 degree, some thickness will be there for that glass plate. So the face where I am not going to grind, it will act as a base. The other face where I will make a polish and I will grind, such that the edge formation, it is having angle 179 degree, and other angle, because even then it is taking a shape of a triangle, the total angle of the triangle should be 180 degree, 179 at this obtuse edge. So the other angles should be of the order of half degree each, that is 30 minute. So single prime is minute. If you use two primes, it will be second. The action of the prism is to produce two coherent images of the given slit. That is, when wavefront from a source fall on this obtuse angle 179 degree, that wavefront divided into two parts. Then from these two polished faces, it get reflected, and two virtual sources are formed. They are coherent, having same color, that is wavelength, same frequency and same amplitude, same intensity. That is what is the principle of using this biprism to obtain two coherent images of the given slit. So the main action is this only. which are separated by certain distance and behave as a two coherent sources. And this is the picture of C. This is a single glass plate. Earlier both faces are plain. Now with the proper grinding, I have made this edge 179 degree. So remaining 1 degree is equally distributed, half degree here, half degree here, 30 minute, 30 minute. And it is kept in this box. We are having a biprism. So when you visit our laboratory, you can see Fresnel biprism, it's written. If you open this, you will find a plate of this kind. If you observe carefully, you are observing one thin line. So that thin line is this 179 degree. So if you put your finger on this side, it is plain, you can feel. And when you put your finger on this side where the 179 edge is there, so this is this portion, something will stretch to your finger. So that is the refracting edge. So that refracting edge on an optical bench you have to mount in front of the light source, so that wavefront coming from the source is divided into two parts. Those two parts will act as a virtual sources which are coherent. Virtual sources, actually they are not there. Virtually you will have, they will behave as a coherent sources. And this is the optical bench. So this is a huge bench. Of course, nowadays we are getting just 1.5 meter length. So in our laboratory we are having around 3 meter in length. Okay, so huge table is required. So this is a monochromatic light source, preferably sodium vapor lamp. In front of that, this is a narrow slit whose width is adjustable. Through this narrow slit, the light is entering, and here one more convex lens is placed so that it is intensified further. So that is falling on the object holder. In this object holder, the biprism is kept with that 179 degree edge towards this lens. So the lens is immaterial. Even if it is not there, it's okay. Just to have more intensity, the lens is kept here. So that single slit light falling on the biprism edge. If you put your eye behind this biprism, you will observe in front of this you are observing a single slit. That is what you are observing in spectrometer in the collimator section. But behind the biprism, if you put your eye, you will observe two narrowly spaced, bright, straight sources. So those sources are S1, S2. We call them as a virtual coherent sources. Okay, and at a larger distance, we are keeping a microscopic eyepiece that will act as a screen. When you observe here, you will observe interference bands. Okay, I will stop at this stage. I will give two videos also. When we meet the offline classes, will if it is possible, I will show this experimental arrangement in the laboratory also, though depending upon how many number of experiments we are going to conduct, it all depends upon how many weeks we are going to get. In other colleges, last semester only 5 experiments they have covered, but we did 7 experiments, right? Okay, all the best, stay home, safe. Okay, we shall see in the next class.